A database seems pretty simple on the surface, right? You give it some data, it holds onto it, you ask for that data back, it gives it to you. So why in the world are there hundreds of different databases out there? Why isn't there just one perfect database to rule them all? Well, the answer, it turns out, is that we're not dealing with one job, but two completely different worlds of data.
Okay, let's just dive right in with a great analogy. Think about it like this. On one side, you've got a Formula One pit crew. Their whole job is transactional. It's all about ultra-fast, super precise operations on one single thing. Get in, change the tires, get out. Fast. On the other side, you have a geologist. Their job is analytical. They're surveying a huge, vast landscape looking for really broad patterns. Now, these two jobs need completely different tools, and it's the exact same story with databases.
So here's how we're going to break it down. First, we'll explore these two worlds of data from a high level. Then, we'll dive deep into that pit crew challenge, finding a needle in a haystack. We'll look at the two main ways to do that, B-Trees versus LSM-Trees, before we switch gears and see the totally different approach of the geologists. And finally, we'll wrap it all up by figuring out how to pick the right tool for the job.
All right, so let's start by putting some official names to these two worlds. They're called OLTP, which stands for Online Transaction Processing, and OLAP, for Online Analytical Processing. Yeah, they sound kind of similar, but trust me, their jobs could not be more different.
This table really just lays it all out. On the left, you've got OLTP systems. These are the engines that run our everyday apps. Notice the patterns here. Lots of small reads, really fast writes, and it's always showing you the absolute latest state of the data. Now on the right, OLAP is all about business intelligence. The queries are massive. We're talking aggregating millions of historical records to answer those big picture questions like, hey, what was our total profit from avocado sales in the Western region last year?
And you just cannot run those huge analytical queries on your main transactional database. That would be like asking the pit crew to stop what they're doing and conduct a full geological survey in the middle of a race. The whole system would just grind to a halt. And that's exactly why companies create a separate copy of their data in a special database called a data warehouse, which is built for one thing and one thing only: analytics.
Okay, so let's focus on the world of the pit crew for a bit, those OLTP systems. Their main challenge is actually really simple to say, but it's incredibly hard to solve.
Imagine a database with 1 billion records, and honestly, that's not even that big these days. If you needed to find just one user's profile, scanning that list from top to bottom would be catastrophically slow. I mean, your app would be completely and utterly unusable.
So here it is, the multi-billion-dollar question. How do you find that single tiny needle in a billion-strand haystack and do it in milliseconds? You obviously can't scan everything. You need a shortcut.
And that shortcut is called an index. It's really just like the index at the back of a textbook. Instead of reading the whole thing to find a topic, you just look it up in the index and it tells you exactly what page to go to. But, and this is a huge but, here's the crucial trade-off. An index makes your reads way, way faster. But because you now have to update both the data and the index every time you write, it makes your writes slower.
And this brings us right to the heart of how database engines are actually designed. Over the past few decades, two major philosophies for building these indexes have really come to dominate. They are both absolutely brilliant, but they come at the problem from completely opposite directions.
This slide just nails the two approaches. On one hand, you have B-Trees, which are like a super meticulous librarian. When a new piece of information arrives, the librarian finds the exact right spot on the shelf and files it away perfectly. On the other hand, you have something called log-structured merge trees, or LSM trees for short. They're like a speedy journalist who just scribbles down new notes on the next blank page in their notepad. The data gets written down fast, and all the organizing happens later on.
So let's look at the journalist method first. When a write comes in, an LSM tree just adds it to a list that's sitting in memory, which is crazy fast. Once that list gets full, it gets written to the disk as a new sorted file. Then, over time, there's a background process that tidies everything up by merging all these little files into bigger, more organized ones. The key idea here is that the database is always just adding to the end of a log, which is basically the fastest possible way you can write to a disk.
Now the librarian, the B-tree, does the complete opposite. It sees the database as a collection of fixed-sized pages, kind of like a book. To change something, it has to find the right page, load it into memory, make the change, and then write that entire updated page back to the exact same spot.
This update-in-place model has been the gold standard in databases for decades. So what's the real trade-off here? Well, LSM trees are much faster for writes since they just append data. But your reads can sometimes be slower because the database might have to check a few different files to find the data you're looking for. B-trees, on the other hand, usually offer faster, more predictable reads since any piece of data only ever lives in one place. But their writes are slower and they cause something called write amplification, which basically means a single tiny change from you might force the database to do a whole lot of extra work behind the scenes.
Okay, let's leave our pit crew behind. We are now entering the world of the geologist, the world of analytics. And in this world, the problem we're trying to solve is completely different, which means it needs a radically different solution.
See, in this world, we are no longer looking for that one needle in the haystack. No, now we are trying to weigh the entire haystack. We don't care about one individual record. We want to scan millions of them to calculate something like a sum or an average. And for this kind of job, those indexes we just spent all that time talking about, they're pretty much useless.
To really get why, we have to look at how data is physically laid out on a disk. So traditionally, databases are row-oriented. This means all the data for a single sale, the date, the product, the store, and the price, is all stored together in one chunk. This is great when you need to pull up everything about that one specific sale.
But for analytics, man, that is just terrible. If your query only cares about the price column, a row-oriented system still has to load all the other columns for every single row, which is a massive waste of time and effort. So analytical systems do something brilliant. They just flip this whole idea on its head. Instead of storing by row, they store by column. All the dates go in one file, all the product names go in another, all the prices in another, and so on. This is called columnar storage.
And this is a total game changer for two big reasons. First, a query that only needs the price can now completely ignore all the other columns, which saves a huge amount of work. And second, if you think about it, data within a single column is often super repetitive. Like a column of product names might just be banana and apple over and over and over. This repetition allows for incredible data compression, which makes the data smaller and even faster to scan through. So we've journeyed through two very different worlds, each with its own set of problems and its own clever solutions. And this brings us to what is probably the most important takeaway of all. The crucial point is this: there is no such thing as the best database. There's only the right tool for the job. So first, you have to define your workload. Are you a pit crew running transactions or a geologist doing analytics? If you're a pit crew, you then have to understand your specific trade-off. Is your app mostly doing reads or is it mostly doing writes? And that choice will naturally lead you to your philosophy. Do you need the meticulous librarian or the speedy journalist? You know, there's this fantastic German proverb that just perfectly captures this whole tension. It says, if you keep things tidily ordered, you're just too lazy to go searching. And that's really the core question, isn't it? Do you pay the cost of organization up front, like the librarian, to make finding things easy later on? Or do you just get the data down fast and accept that searching for it will be more work, like the journalist? It's a fundamental choice in how we manage information. And all of this leads to one final thought. We've gone from these one-size-fits-all databases to these incredibly specialized engines. But our datasets are still just exploding in size, and the questions we're asking are only getting more complex. So what comes next? Will these two worlds we've talked about finally merge into one, or will they specialize even further? What will the next great database engine even look like?